In today's lesson, we will master exponents and logarithms, specifically focusing on rational exponents, logarithmic laws, and solving exponential equations. These concepts are fundamental to the IB Diploma Mathematics Analysis and Approaches syllabus. They appear frequently in both Paper 1, where you'll need to manipulate expressions without a calculator, and Paper 2, where you'll solve complex modeling problems. Mastering these will give you the tools to handle growth and decay, financial math, and calculus. By the end of this video, you will be able to fluidly convert between radical and exponential forms and use logarithmic identities to solve equations that once seemed impossible. We begin with rational exponents. A rational exponent represents both a power and a root simultaneously. For any positive real number a, the expression a to the power of m over n is defined as the nth root of a all raised to the power of m. Think of the denominator n as the root of the operation, and the numerator m as the strength or power. Crucially, for IB examinations, remember that if the root n is an even number, the base a must be non-negative to ensure a real result, and we typically refer to the principal or positive root. Let's apply this to a concrete number. Evaluate 16 to the power of 3/4. Following our rule, the denominator 4 tells us to take the fourth root, and the numerator 3 tells us to cube the result. We calculate the root first because it keeps the numbers smaller and more manageable. The fourth root of 16 is 2, because 2 times 2 times 2 times 2 equals 16. Finally, 2 cubed is 8, so 16 to the power of 3/4 simplifies to 8. In an exam, always look to simplify the root first to avoid calculating large powers like 16 cubed manually. Next, we move to logarithms. The most important thing to understand is that a logarithm is simply the inverse operation of exponentiation. If we have an exponential statement, like y equals a to the power of x, this is equivalent to saying that x is the logarithm to the base a of y. Visually, if you look at the graph of 2 to the x and its inverse, log base 2 of x, you will see they are reflections of each other across the diagonal line y equals x. This reflection is a hallmark of inverse functions in the IB syllabus. For these to be defined, the base a must be positive and not equal to 1. From this definition, two identities follow. Log base a of a equals 1, because a to the power of 1 is a, and log base a of 1 equals 0, because any positive base to the power of 0 is 1. To manipulate more complex expressions, we use three fundamental laws of logarithms. These laws are the direct counterparts to the laws of exponents. First is the product law. The log of a product is the sum of the logs. For instance, if you have log 24, you can split it into log 8 plus log 3. This is useful when you need to break down numbers into their prime factors. Second is the quotient law. The log of a division is the subtraction of the logs. So, log base 3 of 10/4 becomes log base 3 of 10 minus log base 3 of 4. Finally, the power law. This is perhaps the most powerful tool for solving equations. It allows you to move an exponent down to become a multiplier in front of the log. Notice how log base 4 of 3 to the 5th power becomes 5 times log base 4 of 3. This effectively brings the variable down to earth when the variable is in the exponent. Sometimes you will encounter logarithms with different bases that cannot be directly combined. In these cases, we use the change of base formula. This formula allows you to change a log in base a into any new base b. In the IB curriculum, we usually choose base 10 or the natural logarithm, base e, which we write as ln. Let's look at an example. Evaluate log base 25 of 125. Since both 25 and 125 are powers of 5, we can change the base to 5 to simplify the calculation. Now we ask, 5 to what power is 125? The answer is 3, and 5 to what power is 25? The answer is 2. So the final answer is 3/2. This technique is essential for Paper 1, where you must simplify these without a calculator. Now we apply everything to solve exponential equations. There are two primary strategies you need to master. The first method is equating bases. If you can express both sides of an equation with the same base, such that a to the power of f of x equals a to the power of g of x, then the exponents must be equal. Let's solve 1 over 3 to the power of x equals 9 to the power of x plus 1. We recognize that both 1/3 and 9 are powers of 3. 1/3 is 3 to the negative 1, and 9 is 3 squared. Applying the laws of exponents, we multiply the powers. On the right, remember to distribute the 2 to both x and 1. Since the bases are now the same, we set the exponents equal. Subtracting 2x from both sides gives negative 3x equals 2, so x equals negative 2/3. This method is fast and efficient when common bases are obvious. When bases cannot be easily equated, we use our second method, taking the natural logarithm of both sides. This is a universal method that works for any exponential equation. Consider the equation 2 to the power of x minus 1 equals 10. There is no simple integer power that turns 2 into 10, so we take the natural log, ln, of both sides. By applying the power law we learned earlier, we can move the exponent x minus 1 to the front. Now, we isolate x. First, divide both sides by the natural log of 2. Finally, add 1 to both sides to find the exact value of x. In an IB exam, you might be asked for an exact answer like this, or a decimal approximation using your calculator. Using the change of base rule, we can also write this solution as log base 2 of 10 plus 1. Let's tackle an authentic IB-style question. Solve the equation 9 to the power of x minus 3 to the power of x plus 1 minus 10 equals 0. At first glance, this looks like an exponential equation, but notice the relationship between the terms. 9 to the x is equal to 3 squared to the x, which is 3 to the x squared. 9 to the x is actually 3 to the x squared. This is a hidden quadratic. If we let u equal 3 to the power of x, we can rewrite the equation. 3 to the power of x plus 1 is equal to 3 times 3 to the power of x, which is 3u. We also rewrite the middle term using the law of exponents. Now we have a standard quadratic. We factorize this to find the values of u. U minus 5 times u plus 2 equals 0. This gives us two potential solutions for u equals 5 or u equals negative 2. Now we must substitute back to find x. For the first case, 3 to the power of x equals 5. We take the natural log of both sides. X times ln 3 equals ln 5, so x equals ln 5 divided by ln 3. For the second case, we have 3 to the x equals negative 2. Since an exponential function with a positive base can never result in a negative number, this part has no solution. The only valid solution is x equals the natural log of 5 divided by the natural log of 3. Using a substitution is often the most efficient way to solve these quadratic-style exponential problems. Let's look at common pitfalls students encounter in IB exams. A very frequent error is treating logarithms as if they distribute over addition. Remember, the log of a sum cannot be simplified this way. Only the log of a product splits into a sum. When equating bases, students often forget to distribute the multiplier to every term in the exponent. For example, when changing 9 to the x plus 1 into 3 squared to the x plus 1, the result must be 3 to the 2x plus 2, not 2x plus 1. Students often provide solutions that result in taking the log of a negative number. Always check your final answer against the original equation to ensure the arguments of all logarithms are strictly positive. Ensure you distinguish between the log of a squared value and the square of a logarithm. The power law only applies when the exponent is inside the log's argument. To maximize your marks in the IB exam, keep these strategies in mind. First, when you identify a quadratic-style equation, explicitly state your substitution, such as let u equals 3 to the x. IB examiners award method marks for this even if you make a calculation error later. Second, in Paper 2, avoid rounding intermediate steps. Keep your answers in terms of natural logs as long as possible. Rounding early can lead to accuracy errors, which will cost you the final answer mark. Third, always look for solutions that must be rejected. As we saw, exponential functions are always positive. If you get a result where an exponential equals a negative number, clearly state that there is no solution for that branch. Finally, when taking the natural log of both sides, use brackets around the original expression. This prevents you from forgetting to apply the power law to the entire exponent, which is a common way to lose easy marks. It is time to test your understanding. Please pause the video and attempt these 3 questions. The easy question asks you to evaluate 27 to the power of 2/3. The medium question requires you to combine logarithms using the product law to solve for x. The hard question involves a hidden quadratic structure. Take your time to substitute and factorize. Take a moment to work through these now. Pause the video. Let's start with the easy question, 27 to the power of 2/3. The denominator 3 means we take the cube root of 27, which is 3. Then we square that result to get 9. For the medium question, log base 2 of x plus log base 2 of 4 equals 5. Using the product law, we combine the logarithms into a single term. Now, we convert the logarithmic form back into exponential form. 2 to the power of 5 is 32. Dividing by 4 gives us x equals 8. Finally, the hard question, 5 to the power of 2x minus 6 times 5 to the x plus 5 equals 0. This is our hidden quadratic. Let u equal 5 to the power of x. We factorize this expression. This gives us u equals 5, or u equals 1. If 5 to the x equals 5, then x must be 1. If 5 to the x equals 1, then x must be 0. Both solutions are valid as they result in positive arguments for any potential logs. Here are the key takeaways from today's lesson. First, remember that rational exponents combine powers and roots. Always evaluate the root first to keep numbers manageable. Second, logarithms are the inverse of exponentiation. They allow us to solve for variables trapped in exponents. Third, the 3 laws of logarithms, product, quotient, and power, are your primary tools for manipulating equations and expressions. Fourth, use the most efficient strategy. Equating bases is faster for simple powers, but taking the natural log works for every exponential equation. Finally, always be on the lookout for hidden quadratic patterns where one term's exponent is double another's.